So let's finish up with cold integration. Okay. Area region lies in the first quadrant between those two curves. Remember, area is just a double angle, and so integrate over the region VA. Two curves, x squared plus y equals 36, and x squared minus 6x plus y squared. 5. Start with that. I also want my legends. Expressions. Let's see how that looks. Right, so it clearly didn't go out far enough. Ah. And so the region, the area we're looking for, is between these two curves. Right here, right? So now the question is, how are we going to describe that region? Clearly, polar would be beneficial. So start with theta. Right, so in this case for polar, you're not looking at like vertically or horizontal. You're looking at a radial bar. And so it's doing this. So what is that rotating through?
Here's pi over 2.
Near pi over 2. As the bar rotates over that, remember, we only want this region. What does the bar extend from?
Zero to 6.
So I do agree with the to 6. 0 would include what's in here. So I said just this region here, right? So just that region will go yellow to green, right? So yes, I do agree that green is r squared equals 36, r equals 6. What's the yellow?
Is it square root of 6x plus x, minus x?
First convert to polar. What are you going to say?
I was going to say the radical is 6x minus x squared.
Remember, it has to be in polar. So if you convert to polar, r squared minus 6r cosine theta is 0. Solve for r. In fact, got an r right. R times r minus 6 cosine theta is 0. That gives you two options for r. R is 0 or r is 6 cosine theta. R can't be 0 because that's the origin. That means this curve in polar is 6 cosine theta. Like, so equals 0 corresponds to the origin, which clearly this curve is not the origin. Right, so it goes from 6 cosine theta, which is the yellow circle, to 6, which is that quarter circle, the green quarter circle. Our integrand is 1, so that doesn't do anything. And then dA becomes R. drd theta. There is the setup. There's the iterated integral to find the area. Now it's just a matter of evaluating it. Well, notice what's happening in this case. Definitely no theta in the integrand, right? But does R depend on theta? It does. That means we can't do what we did before. We have to integrate with respect to R first. Oops, the R. Antiderivative of R squared over 2. Evaluate that, R equals 6 cosine of theta to the 6. Get that? Back out 36. How would you go about evaluating that? Not negative sine squared. That's positive sine squared. And sine squared minus, sine squared plus cosine squared equals 1. Subtract cosine squared. So that's a good start. How would you evaluate sine squared? Numbers that are integrals.
Negative cosine 2 theta.
How'd you get that?
I don't know.
You're close. That is the reduction identity. So allows you to factor out at 1/2. And that's a simple integral to do now. What is the antiderivative of cosine? Just regular sine. With u sub, you're going to have to multiply by 1/2. Pi over 2 times 2 is pi. What's sine of pi?
0,
What's sine of 0?
0.
That sine term evaluates out to 0. So that whole thing's going to evaluate to just 9 times pi over 2. So there's our area. Now plot this, and then find the designated area. Let's start with plot. In this case, because it was already a polar region, or it was defined in polar plot command. One over 4 cosine of theta. And the other one they wanted was 1. Escape, type in theta escape. Theta, they told us the range, right? Minus pi. That should be all I need. I'm going to go ahead and remove the text because that's kind of annoying. And of course, I'm going to change those hideous colors. I'll still keep the themes. I'll still use a blue and a yellow. not the color that should have been. That's better. Now, what I'm actually going to do here, I think, is I'm going to do something like that, really crop the image because I don't need all of it. That serves my purposes just fine. We want the area inside r equals 1 so inside here, but to the right of 1/4 cosine theta. That would be this region in here, wouldn't it? Finding what r goes from is very easy in this case. But what about theta?
0 to 5.
Zero pi would go
Pi has the 35.
so that would be this. Where does the region start?
2 to 5.
So the region starts there.
Yeah.
That's not where the region starts. You're including too much. I would also include this bit here, which we don't want. We just want this.
Oh.
So once your rotations start there, and you rotate up to there, right? We need those two angles. How do we determine them? Oh wait, sorry, those are the wrong. I drew them in the wrong place. Measured with respect to horizontal, that's what I want. How do we find them? Just find those angles of intersection. Oh, I'm sorry, not secant, but cosine. So where's cosine equal to a quarter? What would be the inverse cosine of a quarter? Right, so that's this one up here. But cosine is even, which means this angle would be the same. But since we're going clockwise, that would be negative. Remember, going clockwise is a negative direction. So negative inverse cosine of a quarter. That is too much to write. I'm just going to call it something else. I'm going to call it psi. So theta goes minus psi to psi. R goes from a quarter secant theta to 1. Notice I'm writing 1 over cosine as secant. Again, the R was easy to see for this one. And area is the integral over the region. And there would be the iterated integral. R squared over 2 is your antiderivative. You divide that from a quarter secant to 1. One minus a 16th secant squared. What is the antiderivative of secant squared? And so theta from negative side to positive side is just 2 times psi. Then you get tangent psi minus tangent of negative psi. Oh, but wait. Isn't tangent odd? So tangent of negative psi is the same as negative tangent of psi. Tangent psi plus tangent psi. That's what that is. Now we have 2 common, factor it out. However, that's not good enough. What did we say psi was?
Inverse cosine of 1/4.
What, minus 1/16. Which can still be simplified. Think back to pre-calculus. Because you should have simplified expressions like that in pre-calculus. Tangent of the inverse cosine. First thing to notice, psi definitely falls in the first quadrant, right? Inverse cosine of a quarter is in the first quadrant. That means it is an acute angle. We can use right triangle trigonometry. Let's call that angle there our psi, the inverse cosine of a quarter. Remember, if psi is inverse cosine of a quarter, what does that mean cosine of psi equals? One quarter. In terms of right triangle trigonometry, how is cosine defined? What's that missing line? Which is what? What's the actual measure? Square root of 15. How'd you get it?
So 1 squared plus 1 is going to be 16.
Right, Pythagorean theorem, a squared plus b squared equals c squared. You have either a or b, depending on how you label them. And you have c, solve for the missing. Square root of 16 minus 1. Root 15. But we want tangent of the inverse cosine. Tangent of psi. How is tangent defined in right triangle trigonometry? What is it? So what is tangent of psi here? Square root of 15. And there's your answer. That would be the area.
If you want to go back to the slide just for one.
This one?
Yeah, I just got to that.
So you followed how I actually determined the bounds, right? Okay, good. Right here. Tangent is odd. Should probably spell out tangent, huh? That substitution that I made is a very common practice. We don't have to keep writing out the inverse cosine of a quarter every single time. So we just define it to be something else. That's easier to write, right? In this case, I chose sine. That is very common. It just reduces how much you're writing, makes it look more condensed and nicer. Do you have to do it? No. But we probably see that used a lot in physics as well. We tend to do that a lot in physics. So they want us to convert that iterated integral into polar coordinates and then evaluate it. Could you evaluate that in rectangular? Yes. You could actually do that in rectangular, but you'd have to switch the order of integration first. But then it's going to be really ugly. Well, actually, I don't know if you will be able to. You will be able to do the first one, but then once you get to the dx, I don't know if you'll be able to do it. That's okay, because we recognize this is actually a polar region. The question is, which polar region? What is the polar region? And this one I will not plot. So what are the bounds for theta? -3 to 0 is the bounds for y in rectangular. We want to write this in terms of polar. Remember, that's dr d theta. And you have to first recognize what polar region this is actually representing.
Is it 2/3 pi?
How are you determining 2/3 pi?
So it's in the quadrant 4.
How do you get quadrant 4? What's your reasoning?
Just because it's the y, I put it in the 4.
Okay, I do agree because y is negative, right? It's definitely below the x-axis. That's 3 or 4. How do you determine it's 4?
Because again, for the x, it's the negative.
So which quadrant is x negative in between 3 and 4?
It's 4, right? Oh, it's 3, sorry.
Quadrant 3. So I do agree, definitely in the third quadrant. What angles are the third quadrant? So negative x-axis to negative y-axis is what? What's the negative x? What angle is that?
Wait, no, but that's radius, right? The 2 pi.
That's the angle. But that 2 pi would be the positive x. Back to the positive x-axis. So what's that angle?
Pi.
What's that angle?
2 pi over 2.
So quadrant 3 incorporates all the angles between pi and 3 pi over 2. So you narrow it down. Now the question is, does this polar region take all of those angles? Or does it only take some of them? Reason myself not plotting this one. This is one that you should recognize. What kind of curve is that?
Semicircle.
Which one?
X equals negative.
Right, so which semicircle? You have 4 semicircles.
Right half.
Left half. X is negative, so to the left. What's the radius?
3.
So just the X tells you that you're dealing with the left semicircle of radius 3. Now use the Y. Y is negative. So that's a quarter circle, right? What quarter circle? You already said it. Bottom,
It's right. Oh, sorry, bottom left.
bottom left of quadrant 3. So then wouldn't that look like this? What are the angles? What did we just say?
Pi is 3 pi over 2.
Oops. Why did I do it now? What's the radius? Where does the radius go from? Or I don't want to say radius. What does the radial bar go from?
Zero to 3.
0 to 3. You now need to write your integrand in polar coordinates. So how would you write y in polar?
R sine 2.
What about x squared plus y squared plus 1?
R squared plus 1.
There's your integrand. Now what does your differential become?
R dr d theta.
There you go, there's your conversion. Now what I'm going to do is I'm going to write it this way. And incorporate that r into the numerator. There's your conversion. Now we need to integrate that. How would you integrate that?
You have to replace with the D line.
Could. not gonna change anything. Why not get rid of that theta first? Like, you have a whole function of r, right? The r squared over r squared plus 1 times just a function of theta. And this is a polar rectangle, so you can just easily flip the order. So you're not wrong if you do that. You could do r first. But then you have to keep carrying that sign through. So why not just get rid of it by integrating with respect to theta first? What is the antiderivative of sine?
Cosine.
Negative cosine. So we're going to have negative. What is cosine of 3 pi over 2?
-1.
0,
0. What is cosine of pi?
-1,
Negative 1. 0 minus negative 1.
0,
Positive 1. But remember, we said the antiderivative sign was negative cosine. That's what we're left with. How would you evaluate that?
Is this interesting?
Because you have an r squared in the numerator. 1 over r squared plus 1, yes, is inverse tangent. But you have an r squared there.
Can we divide everything by this way?
You could, but that's going to leave you with a complex fraction. Right, that would leave you with what? 1 over 1 plus 1 over r squared. Right, and then the problem with that is then you'd have to do a u sub and you can't. Right, your u would be 1 over r, but you don't have that du, which is a shame.
You said 1 over r squared plus 1 is tangent, correct?
1 over r squared plus 1, the antiderivative of that is inverse tangent.
Can we just do r squared times 1 over that then? It's the same function. It's just
Right, but then you have a problem. You don't have it. What's your product rule for antiderivatives? Integration by parts. It doesn't just simply work as what's the antiderivative of r squared times the antiderivative of 1 over r squared plus 1. So to think back to Calc 2. What was the technique for rational functions? Because that's rational, right? How did you do the antiderivative of rational functions?
Partial fraction decomposition.
Partial fraction decomposition. What was the first step of partial fraction decomposition? Which is actually, by the way, an algebra technique. So there's actually like no calculus in that. until you go to integrate it. Because decomposing fractions is pure algebra. I think it's covered in algebra 2. First step has to be proper. What does it mean for a rational function to be proper?
Wherever is on the top has to be wrote as.
What do you mean by whatever's on top?
The numerator has to be wrote.
What about the numerator? That would be for just regular fractions. But a rational number, yes, I agree with that. Right, the value of the numerator is less than the value of the denominator. Right, so 1/2 is proper, 3/2 is improper. With rational functions, yes, something about the numerator has to be small. That has to be smaller than something about the denominator. But what is that value? What is that something? Remember what it means to be a rational function. Polynomial over polynomial. See, it's also a good review of pre-calc. The degree of the numerator has to be less than the degree of the denominator. Is this proper?
No.
So step 1 is make it proper. How would you make it proper? Polynomial division. Oh, but guess what? Your denominator is not linear, which means you can't use synthetic. We have to use long division. But this one's not difficult. In fact, I'll leave you to actually do the algebra. When you divide r squared by r squared plus 1, you'll be left with 1 minus 1 over r squared plus 1. Your quotient is 1, the remainder is -1. Oh, now look at that. Isn't that a nice one to work with? That now actually does not require any kind of decomposition, does it? So while technically, yes, we use the method of partial fraction decomposition, we don't actually have to worry about the partial fraction part. Antiderivative of 1, that's easy. That's just r, right? Antiderivative of 1 over r squared plus 1. Would you say it was? The inverse tangent of what? What would be theta in this case? Would just be r, right? And we go what? R equals 0 to 3? What is the inverse tangent of 0? Zero. Oh, wait a minute. Hold up. Oh no, that works, never mind. Notice I've actually been ignoring a very important rule throughout all of these. I've never really been checking to make sure that your integrand is continuous over the interval. I've just been assuming that it is. In this case it is. And remember, if it's not, then it's improper. And yes, you can have improper multiple integrals. I don't cover them, but they do exist. Both types. So we could have something like this. And those are fun. Yeah, those are fun. Where your region of integration is actually an infinite region. Those suck. I'll leave those for applied courses. The method is really the same. You still have to wind up with limits, and you're just doing it more than once. It's just terrible. So, oh, why did I write -1? Should be -3. All right, that'd be that evaluation. Inverse tangent of 3 minus 3. So also being able to convert to polar from an iterated form is important as well. You may run across cases where we're going to have to do that. Obviously not with two-dimensional. Because obviously if it's a double integral, you're going to be able to see it's polar right off the bat. But when we move on to higher level integrals, you set up the iterated integral and then you realize, so you now get down to the double, and you realize, oh, this is going to be easier in polar. Then you have to convert it from the iterated form into polar. We only go up to triple integrals in this course. The largest integral I ever did was, I think, 26 when I first started studying string theory. That was back when we thought it was 26 dimensions.
How long did that take it?
Oh, I just said, F this. Now I think it's 10. 9 spatial, and then time. What's the highest you're going to have to do? Probably depends on your major.
How about data science? How about data science?
That's a good question. That, ooh, actually, you may actually have to go up above 10, depending. Because with data science, you're dealing with a lot of probabilities. Well, it's going to be multivariate probabilities, because it's usually more than one random variable you have. So it depends on how many random variables you have. If you have 4 random variables, then you're having a 4-level integral. 2 would be a double. 8 random variables would be an 8 level. So that would depend on how many random variables you have. But chances are you're going to be using technology. So you won't have to worry about doing it by hand. But having a strong foundation of how it's being done is going to help you. Yeah, so you probably won't have to do it by hand, but you might have to deal with some high-level integrals, depending on the number of random variables you have. So that's it for double integrals. Questions on evaluating a double integral? You know what that means. Triples are next. Also, you have a quiz that goes up today. That will be due Tuesday. And your exam is next Friday. And the exam does cover triple integrals and general regions, right, which we cover Tuesday and finish it up on Thursday. So the second exam covers everything since the first exam. So motion in space up through triple integrals and general regions. Right. That's all the partial derivatives, by the way, as well as that goes on there. And if I remember correctly, there was a lot of integration. It's just how the RNG happened to run. It did a lot of integration type problems and not a lot of anything else. So your heaviest focus should probably be on multiple integration. But I think that's the toughest part anyway. Right, motion in space should be relatively simple. Partial derivatives itself was relatively simple. It's this stuff that's difficult. And it's a mixture of iterated integrals and here's a region you need to integrate over go. Very much like what we've been working on. So it's going to be a mixture of here's an iterated integral, solve it, and here's a region you need to integrate over, describe the region, set up the iterated integral, and then evaluate. Toughest part is setting up the iterated integral. After that point, you can use a calculator to evaluate it unless the problem tells you not to. And I think there's one on there that does say you can't use a calculator. You have to do it by hand. But otherwise, set it up and then just use a calculator to evaluate it. And you're going to want to bring your calculator because I don't think you're going to be able to finish the exam if you try to do every single one by hand. It's written with the idea of you having a calculator. Again, I'm testing more of, do you understand the region? Can you set up the integral the right way? Not as much of, can we actually evaluate it? That was Calc 1 and Calc 2. If you can't evaluate an integral, you shouldn't be here, is my motto. Because you shouldn't have passed Calc 2. Right? Also, the fourth project is due the 11th, so continue to work on that. The weekend Tuesday is triple integrals.